5.2, log functions. Log functions, which are the inverse of exponential functions. Just like exponential functions, the base of the function can change, and that still is going to be the parent function. So if I have the function of f with a log base b, it would look something like that. Now, one thing we will also get into is natural logs. So first, when I'm doing this, just like this right here, because this is an inverse of the exponential function, we can always rewrite these values. So in this case, if I want to rewrite this, I can also say that this is log base b, x is equal to y. If I want to rewrite this as the inverse, which would be my exponential, you look at what your base is. So my base here is b, right here, this is your base b. And whatever the log is equal to becomes the exponent. Whatever you're taking the log of becomes what it's equal to. Okay? So again, here's an exponential base b, here's a log base b. Those two numbers stay the same. Notice how those two numbers are on the left-hand side. The x and the y change spots. So if I'm looking at this first one, evaluate, and we're not going to be using a calculator. So if I first rewrite this, this is log base 2 of 32 is equal to y. Another way I can think of this now, because my base here is 2, so I can say that this would be 2 raised to the y power is equal to 32. Now, one thing about 32 is that's going to be 2 to the 5th power. So now I have my same base. So since I have my same base here, now I know that y is equal to 5. That is one way that you can do this. Now, another way that you can do this, actually, we're going to do it that way. I want you to pause the video and try to do b by yourself first before I show you the other way. So log base 3 of 1 is equal to y. So my base here is 3 raised to some power is equal to 1. Now this is where you just have to remember your properties of exponents. Any number raised to the 0 power is equal to 1. So y is equal to 0. Now for this, actually I want you to just pause the video and do the other two questions still in that same format. So one of the hardest things about this is knowing your properties of exponents, because when they have log of the inverse of exponents, you know our properties of exponents. So like this 4, I can rewrite the 4 as 2 squared. So that 2 times y gets multiplied. These two bases are the same, so I know that 2y is equal to 1. So y is equal to 1/2 here. Same thing here. Here's my base 10. So 10 raised to the y power is equal to 1 over 100. That's a base 10 of -2, because 10 raised to the -2 power is 1 over 100. This is where people typically, if they struggle, is rewriting the power of exponential. So then that means y is equal to -2. Now, if I look at these properties of logs, we already went over this. Whenever we have anything taking the log of, it doesn't matter the base of 1, that's always going to be 0. That's kind of like this one right here. Whenever we have a log base of that same number right here, this is like to the first power. This right here is equal to 1 because of that power. These two are actually kind of like the same question, because this log base of this a, this will just be equal to x. That's the same thing if my exponential base and my log base are in the same spot. Is just equal to what we have left over. And then my 1-to-1, like we talked about in 5.1, if we have a log base of a log base a on this side and log base a on this side, that means that these two have to be equal to each other. So again, looking at these properties, when I ever take the log of something that's 1, if I want to rewrite that, this is saying 4 raised to something is equal to 1, so that means that value is always going to be equal to 0. Same thing here. This is like this property. Log base square root 7 of square root 7, these essentially cancel out because this is like to the first power. You could think of it like that. So this would be equal to 1. And same thing here. This exponential base with this log base, these two cancel each other out. They're inverses. Just like adding, subtracting, multiplying, dividing. So that answer would be 20. So right now I want you to try to do D, E, F by yourself. So you're getting 12, 1. So those two are the same because they have the same base. Now, can't remember from Algebra 2 or Pre-Calc FST, when there's no base shown, that's always going to be the common log of 10. So this right here, if there's no base shown, the base is always 10. Here, the same, so I add that 6 and then take the square root, we have a positive -4. So now let's actually start graphing. So I want you to pause the video and I want you to graph 2x on this graph for me. We have this. This is our graph of 2 to the x. Now we're going to graph this log, and the best way to graph this log is we're going to say that this equation is equal to y. And we're going to rewrite it because we're going to use this, what we already have to help us. So because this base here is 2, so this would be 2 to the y is equal to x. Again, we already have these values right here. So if I said that my x value and my 2 to the y value, my input output, I'm kind of working backwards. If you see that? Sorry, I feel like that might confuse people, so we erase that part. But here's our input, here's our output. Now, what I want to make sure that you understand is that this is like the opposite. Because these are inverses, remember our domain and our range switch. So my whole domain here is going to become my range over here. So I am just repeating all of these numbers for my range, because my whole range here is my domain over here. If I just repeat all those numbers, now I'm going to plot these points. So my x value would be 1/8, my y value would be -3. So pause the video and plot these points for my log base 2 of x. So here are my points. Here's my graph. Now just like how this one right here has a horizontal asymptote, at y is equal to 0. We still have an asymptote here, but this one has a vertical asymptote at x is equal to 0. So because of this right here, it's saying that this graph is going to get super close to, but never actually touch. And again, because these two are inverses of each other, that means that they're going to be a reflection over the x, y line. If I were to plot my slant asymptote, well, it's not an asymptote, a slant line, this is my reflection line, it's going to reflect over the x equals y line. So it does, because again, these are inverses. So this is my exponential, and this is what my log looks like. We're going to sketch these two graphs. Now, first, before we get into that, we have to be able to look at to see what the transformations that will help us in our life. We still have that h on the inside of the parent function. We still have that k that would move up and down. Now, again, depending on what the parent function is, it's going to change. Now, when I'm talking about this moves it to the right one, that's going to move that vertical asymptote to the right one, just like this. So I already know I have a vertical asymptote at a +1 because of this right here. And then what's my base? My base here is 10. Now, just like if you can't find the numbers, you can go into your y equals, and because the fact that we have a common log of 10, that's this button right here. This is my common log 10. And I have my x minus 1. So I could go to my table and I could plot these points. Notice how right here I have all those arrows because we have that vertical asymptote. So pause the video and plot those points. So it doesn't have to be super pretty, but looks something like this. Again, hugging that asymptote, but never actually crossing the asymptote. It's also asking for my domain. Now, because of my domain here, we have this restriction at +1. I'm going from 1 and to infinity. When I look at my range, there's no restriction on my range. I'm going to go on forever slowly, but surely, and I'm going down forever. So my range here is going to be all real numbers. And my asymptote will be my vertical asymptote at x is equal to +1. So right now, I want you to plot B by yourself. So this is moving it up to. So what are we actually moving up to? This point right here that typically is going to start at that spot. But again, if you can plug this into your graphing calculator, you should get this other point to help you with the direction and getting hugging that asymptote. So that vertical asymptote at 0. Domain is from 0, not including 0, to infinity, and my range all real numbers. So now we have this natural log function. This right here is my natural log function. In the natural log function, my base here that we typically don't write is e. Again, that e that goes on forever. So the properties for natural log are the same properties of our other log function. So like for this example here, this has a log base e. We typically don't write that, but I can rewrite 1 over e as e to the negative 1. And because these two bases, because this or my log base and exponential base are the same, this cancels out. My answer here is just negative 1. I want you to pause the video and try to do B, C, and D by yourself. So you should have gotten 5 because these two have the same base, cancel. You should have gotten 0 because this becomes 0 on top. The log of any number that's 1 is equal to 0. So 0 divided by 3 is 0. And here, base e with exponential e, this is just like a 1 then. This number becomes 1, which is 2. So find the domain. So again, that domain is when we look back up here, is when I move left and right. That's going to move my vertical asymptote. So when I'm looking at this right here is going to move it to the right 2. Because I did not have any reflection, this will give me a domain is equal to 2 to infinity. So right now I want you to try to do B and C by yourself. Be careful. So for this one, you have to get this to be a positive x. So if I factor out that negative 1, what I actually have here says x minus 2. So this is also moving to the right 2. Okay, it's going to be flipped because of that, but my domain here is going to be, again, to the right 2. Now this right here, when I'm looking at my domain, another way you could do it is saying that this equation, that's 2 minus x, has to be greater than 0. Okay, 2 minus x has to be greater than 0. So if I did that here, I would subtract the 2, divide by negative 1, I would still get that 2. If you want to choose to do it that way, that's fine. So if this x squared has to be greater than 0. Well, if I take the square root of that, x has to be greater than 0. So when I look at my domain, the only restriction I have is 0 because it's not equal to 0. So this would be from negative infinity to 0, union 0 to infinity. Right now, I want you to read this and answer A, B, and C by yourself. You are smart. You can have the capability to do that. I know it. So all this question is asking you is, here's this human memory model, which is pretty cool. So on the day of the test, the average test score was 75% when listening to several lectures in a row. 2 months later, that average score went down to 68.41. And then after a half a year, so that's 6 months, that's what you know is 6 months, be 63.33%. And there you have it. Bing, bada, boom. You're smarter than when you started this. Trust me, you are. Have a grand, have a wonderful day.